Okay, for this first concept, we're talking about square roots. A number is a square root of another number. A is a square root of B if when you square A, you get B. So 7 is the square root of 49 because when you square 7, 7 times 7, you get 49. Okay? And we are going to use some certain terms. This is called the radical symbol. And that we're going to use that to come up with a non-negative square root at this point. We will eventually come to see that, for example, -7 times -7, negative times negative is positive, is also 49. But for now, we're going to be always talking about the principal square root, which would be the positive square root. Okay? And we call the number that's underneath the radicand. So we have a radical symbol, we have a radicand, and we have square roots all through this. Those are terms we'll be using. Okay, so we are simplifying square root expressions, and the first one here, the idea is what is the square root of 81? And what you're looking for here, like it says here, is how do you find a square root? You find a number that multiplies by itself to get the radicand, the number under the radical symbol. So what number times itself equals 9, or equals 81 rather? It's 9. Okay? And what about for the square root of 9/16? Well, what number times itself equals 9, and what number times itself equals 16? 3 times 3 is 9, and 4 times 4 is 16. So you can say 3/4 times 3/4 will give you 9/16. So you have to square 3/4 to get 9/16. So square rooting 9/16 gets you 3/4. Quick trick here that you can see is that since it's numerator times numerator, to get the numerator, you can square root the numerator and denominator separately. Square root of 9 is 3, square root of 16 is 4. Okay? Here's your got it problem. So the square of an integer is a perfect square. Numbers that are perfect squares, when you square root them, you get an exact integer value. 49 is a perfect square because 49 has a square root of 7. 7 squared is 49. Okay? When the radicand, the number you're square rooting, isn't a perfect square, though, you can estimate it. And here's how you estimate it. Okay? There's this example here, the real world example, where lobsters have these little square regions on their eyes, and a scientist, a biologist, measured and calculated that the area of that is 386 square microns. Microns are very small units of measure. Okay, so what's the approximate side length? Well, remember that squares are same length and width. So some number times itself would give you that area of 386. So what number times itself gives you 386? We're looking for the square root of 386. And the way that we're going to do it is we're going to find what two perfect squares it is most closely in between, okay? So what is the square root of 386? Well, let's take two numbers that we know are perfect squares that are on either side of 386. 361, that's 19 squared, and 400, that's 20 squared. 386 is right in between there. Now you can check this. One way to check it is to say, okay, I'm going to just try a number. First, like what's 10 squared? 10 squared is 100, and 100's not big enough. We're going to go bigger. So let's try 20 squared. What's 20 squared? 20 times 20 is 400. Now that's pretty good. So now we know that we are way bigger than 10, but pretty close to 20. And we can kind of guesstimate what numbers we need to square to check. Okay? And it falls right in between these two. It's a little closer to 20 squared, so we say it's roughly 20 microns on a side. Here's your got it problem. You can classify numbers by the characteristics that they have. Some types of numbers can be represented on the number line. Now we're going to spend this next couple minutes classifying numbers, and we're going to put them in sets. You can classify numbers using sets. A set is a well-defined collection of objects. Well-defined means we know when it's part of the set and when it's not part of the set. It's very clear that it either is or isn't. Of course, you have to understand it, but once you do understand it, you can clearly say whether something's in that group or not. Each object in the set is called an element. So all of the elements together make up the set. And of course, some elements in the set can become a subset of that given set. Okay? So you can say, if I had the set of all of the students in Massey's algebra classes, a subset of that would be all the kids just in Massey's 1W algebra classes. Or another subset might be just the boys in my algebra classes. Okay? So you can write braces around the group to indicate that this is a set. And here's a summary of the concept that we will get to more in a minute, but these are the different types of groups, and I'm just going to point out really quickly. For the real number system, and that's the only kind of numbers you're going to be working with, imaginary numbers are for another course, but you are either, well, if you're a number, you are either a rational number, of which there are these types, or you're an irrational number. You can't be both. You are either rational or you're irrational. And we're going to learn what makes up each type of number in just a second. This is just a general concept summary. The real number system can be split up into two subsets. The first subset we're going to talk about is the rational number group. And the rational number group is any number that you can write in the form of a ratio. The word rational is based in the word ratio, as you can see there. Ratios are written in the form of a over b, where those two numbers, a and b, are integers. And you can't have b be 0, but you're not allowed to divide by 0. In mathematics, it gives you errors when you try to divide by 0. So it's not allowed. It's undefined. Okay? Now, what does it mean to be a rational number? Well, what constitutes that? If there's a decimal number and it terminates, it ends after a certain number of digits, then you can write that as a ratio. In fact, in this one, it goes out to the hundredths place, so you can take the digits 545 and put it over 100 because it goes to the hundredths place. So 545 hundredths is equivalent to this. That's a ratio of two integers. We'll get to integers in a second. You can also do the same thing with decimal numbers that repeat. So 0.416 repeating, which you can write like that with the bar over the top of the set that repeats. That can be written as a ratio as well. So we call it a rational number. Okay? Now, that's a general rational number, but there are more specific rational numbers, and these should be identifiable to you. Natural numbers. Any number that starts at 1 and goes by 1 upwards, like you're counting. You count things starting at 1. 1, 2, 3, 4, 5, things like that. Natural numbers. If you include 0 in the set, then you are talking about whole numbers. So whole numbers is 0 and all the natural numbers. 0, 1, 2, 3. Okay? Anything that's a natural number is also a whole number. And whole numbers are just the 0 and positive integers. Integers are, again, from 0, whole unit jumps from 0 in each direction. So all of the negative numbers and positive numbers of the form of like -5, -4, -3, -2, -1, 1, 2, 3, etc. Those are integers. Get to know that word because you really need to know and understand what that word is. Okay? So if it's a natural number, it's a subset of the whole number group. And if it's a whole number, it's a subset of the integers. And integers are a subset of rational numbers because you can imagine all of these numbers. You could just simply take any number and put it over 1. Right? 3 over 1 is equal to 3, and now it's written as a ratio. Yep. So that's rational numbers. And remember, decimals that repeat or terminate are also rational numbers. They're just not part of these subsets. If it's not a rational number, it's an irrational number. And we don't have any designation for any uh, irrational numbers, no subsets. Just call them irrational numbers. Now, a fun thing to point out here is that if you have square roots, if the number is a perfect square, the radicand is a perfect square, then you can just turn that into its square root. Square root of 4 is 2. So that's actually rational. Square root of 25 is just 5. That's actually rational. But when the radicand is not a perfect square, it won't work out as a nice, neat integer square root, and that will be irrational. It'll go on forever without repeating or terminating. Okay? Together, the rational numbers and irrational numbers make the real number set. All right, so what if we wanted to classify numbers in these groups? And by the way, I've recopied this for you for convenience. You might want to make some notes so you have reference to this. Okay? To which subsets of the real numbers does each number belong? And there's a little hint over here. How do you classify it? You can look for negative signs, fractions, decimals that do not terminate or repeat, and radicands that are not perfect squares. Those will all be hints for you of where they go. Now, if we look at this one, 15, what group is that in? Well, 15 you can imagine as like a counting number. You can count up to 15 if you're counting items, and that puts it in the natural numbers group. And a cool thing about that is that once you know it's in the natural numbers group, you know it's in all of these larger groups as well, okay? So we already know they're all real numbers, so we're not going to call it real numbers, but we can say then that 15 is a natural number, and then of course then it means it's also a whole number, it's also an integer, and it's also a rational number, okay? What about the next one, negative 1.4583? Well, it is clearly not in the counting numbers, whole numbers, or even integers group, because these are like what you informally would call whole numbers, positive and negative, right? Whole numbers are more specifically not integers. We are going to use integers from now on. But it does terminate, okay? And any number, any decimal number that terminates, even if it's negative, as long as it ends somewhere, we can write it as a rational number. So we can call that rational. And finally, we have this square root of 57. Now, what are the perfect squares on either side of it? Square root of 49 is 7. Square root of 64 is 8. So it's between 7 and 8, but it's not a perfect square. And anytime you're square rooting a number that's not a perfect square, that doesn't work out to be an integer, is going to be irrational. So this number is irrational. Got it? If you do got it, let's see if you can do the got it problems. Categorize these as well. Okay, so we can compare two different real numbers with different values with greater than, less than, or greater than or equal to, less than or equal to symbols. You should be familiar with this. If you're not, we can talk, but this is a skill you should have at least come having some familiarity with. And the question then they ask is, how do these two numbers compare? Which one's greater? And how will we do this? Well, we're going to do it like this. Okay, I'm going to show you what I did here. We want to turn them into the same form. If you're not using a calculator, it's going to be difficult for you to square root this. You know that this is a little more than 4 because square root of 16 is 4, but is that going to beat this or not? So what I'm going to do here, what I've done here is turned this into an improper fraction, and then I squared it. And when I square it, I square the top, square the bottom, get this, turn it into an improper fraction with this math here, and find out that this squared is this. So the square root of this is exactly the same number as this is. Now, if this is confusing to you, it's because I'm rushing through it and I will answer questions. But essentially, I can write any number as the square root of its square. So I've squared this and said the square root of what I get when I square it will be that. So I can now compare these two, square root of 17, square root of 18, and 7/9. Which one's greater? Clearly, because 18 and 7/9 is greater than 17, the square root of 18 and 7/9, which is that, is greater. Okay? So here's your got it problem, and I am going to actually talk you through this, but I want you to actually try and do it on your own first. Remember what I said. You can rewrite this as a square root by multiplying it by itself and then putting that under the radical. So try it like that and compare the two and see if you find out which one is greater. All right. So what we're looking at here is I have done the math over here to square 11.52. 11.52 times 11.52, and I get this number. That means if I put that under the square root symbol, it'll be exactly this. Okay? Since 11.52 times 11.52 is 132.6104, then the square root of that will be the number, 11.52. Now it's easy to compare. Which is bigger, 129 or 132.6104? And clearly that one's larger. So as you can see, we can write it like that. All right, so one thing that we can do is we can graph and order real numbers on a number line. And the problem that they're asking us to do here is, what's the order of these numbers? Square root of 4, 0.4, negative 2/3, square root of 2, and negative 1.5, from least to greatest. So how can we do this? Okay, well, one thing that I know straight off the bat is that negative numbers are always smaller than positive numbers. So these two right here, negative 2/3 and negative 1.5, are going to be the lowest ones, right? Now, which is lower? Well, this is between 0 and negative 1, right? It's less than 0, but it's not quite negative 1. It's only negative 2/3. It's going to be between 0 and negative 1 right here. And this one is further than that. It's 1.5 units. So it's between negative 1 and negative 2. So I already know that I've got a value at negative 1.5 there, and another one here at negative 2/3. In between the whole numbers, negative 2 and negative 1 for this one, and between negative 1 and 0 for this one. Now, if I keep going, square root of 4, 0.4, and square root of 2. Well, 0.4 is between 0 and 1. So I know that there's going to be a point there between 0 and 1. And I also know that this square root of 4 is exactly 2. So I'm going to have a point right there at 2. And square root of 2, just like we were estimating, this is between the square root of 1, which is 1, and the square root of 4, which is 2. That's going to be between 1 and 2. So we've got a point there for 0.4. We've got another point there we have a point here for 0.4. We have a point here between 1 and 2 for root 2, and we have a point here exactly at 2, which is the same as root 4. Okay? And as you can see, putting all those numbers in place, that's the order that we get. So which one has that correct order to it? That is going to be answer C. So there you go. Here is your got it problem. If you so choose, you can take a shot at these lesson check problems and then restart the video to check your answers. Good luck.